We have a new member, Jean Barrera, and she is online with us tonight. She's the one with the motorcycle, it looks like, down there. Welcome, Jean.
Welcome.
Hey, it's Key. I'm John.
Oh. I was going to say, that does not sound like a womanly voice.
So, Jean, are you there? Can you talk?
Is it?
Yeah. So it's John. I met a couple of you guys over at the reservoir a couple nights ago.
Oh, cool.
Yeah, hey, John. How you
Pronunciation.
Okay, I'm bad, forgive me.
It's all good. It's all good.
I'm
No
just looking
problem.
at a piece of paper here and trying to figure it out, but welcome. And how did you learn about EAS?
Well, honestly, I found it on an old Reddit post. I was looking for information on telescopes, and yeah, I found the post, found the website, and yeah, I showed up at the reservoir one day. Started asking a bunch of questions.
Very cool. Very cool. Well, welcome.
Okay.
Yeah.
Nice to see you here.
Yeah, nice bike.
Thank you.
So, John,
So,
are you the fellow with the 10-inch black Dobsonian that was there the other day?
Yep, that was me.
Oh, okay, very good. I know who you are.
Excellent.
Cool.
So besides having a little wing ding here on Saturday night, I don't have any other business.
Okay, well, that's a pretty major
Wing ding?
major throwdown on Saturday night. So
It's a wingding.
It's a
a
wing
wing
ding.
ding. Okay.
I had a question about posters. Is it okay? I have like a couple extras. Can we staple them onto a telephone pole, or you want to do that?
I don't see why not.
I say go ahead.
Yeah, if it's an appropriate place to staple them, sure. Go
I just say be sure to clean it up after the star party.
Okay.
We'll have the police will come after us for unlawful association or something.
Yeah,
You
well,
can't-
Chris-
you can't do-
Laws.
You can't look through telescopes here. We don't allow that kind of stuff in this town.
well, all I know is that Christine, you or that other gal got ahead of me and put up posters in my section.
Uh-oh.
When we divided up Southwest, I thought that we were pretty clear. But anyway, you had there were posters everywhere that I was supposed to put them up the day before
I only
yesterday.
put one in. I only put one. I realized after looking at it in your area. So I don't know about any.
Aneta. Yeah, I think I only infringed on the hamburger place and the library. I was at the library yesterday and there was none there, so I put it at the library yesterday.
Well, all
I
right.
also found posters where I was supposed to go, so I thought it's okay, it's fine, not a big deal.
We've
Well,
got
I know we're going to discuss Dexter after the presentation, but I think it's kind of a long one, Andy, because
I will try to go as quickly as possible, which may mean that some of the sciencey stuff gets left behind. So
I'm okay with that.
I suspect a lot of people will be okay with that as we get into it. So
Well, you want to get started?
yeah.
So
let's
Dan,
go
I have a
ahead.
quick question. Dan,
Mhm.
should I go down the list and double check a couple places?
I don't think we need to. I already went down the list, and everywhere that I went that was mine and outside mine was already posted. So
Oh,
Okay, so let's get started on the presentation. We can talk about Dexter later.
I have a
Andy.
quick question. One question. Can I see
Mhm.
your shirt, Ken? Woohoo! The first. Yeah, that looks nice. That's really nice.
it'd be great
Wow.
if he said something so that Ken say something so that the screen takes over for you. I guess I can navigate and find you.
I'll just,
Okay, how about this? How about this?
Oh,
There we
yeah.
go.
Nice.
Yeah.
Excellent.
I had it printed backwards on purpose.
Wow. No, it only displays back. We see it.
If I did print it backwards on purpose, it would show up correct. Did anybody get my mailing about all this?
Yes.
yes.
Thank you, Ken.
Yeah, so you've got all the details on how to
Looks great.
But I would definitely suggest you bring your own piece of clothing because it will be a lot quicker turnaround than they've got some stuff over there, on the rack, but be a lot quicker than having them order something for you.
Now, is that ink on your forearm? Is that also a club logo? I never saw that you had a tattoo. What do you got there?
Right there.
Yeah.
Where is it here?
Oh, what?
There it is.
Nice.
How do I make this work?
There you go.
There you go.
I see stars and fractals.
That's right. I've got a hole in my arm, you see, with the.
Huh,
Nice.
wow.
Very nice. All right.
Okay.
Yeah.
Andy,
Yes.
I hear you have a presentation tonight.
Are we ready?
We are very ready.
Right,
Okay. Well, I'm going to pause this. And everybody see that?
Yes.
Oh, wow. We have mastered the technology. Okay. Australopithecus can learn something. So I was ready to give this program last month when it actually was a little fresher in my brain because I'd just written it. And of course that didn't happen. So I'm going to jump in here. It would have been a little more timely last month because the globular cluster season really is a little bit past. You really want to get to that around mid to late June. But we're gonna go ahead and still have some time after this to get into the heart of the globular cluster season, observing wise. But that was the main reason why I chose the topic. And my forward isn't working. Okay, we'll have to do it this way. Okay, so globular clusters really, the height of the season is in midsummer for reasons that we'll talk about a little bit later, and they really are kind of the most physically homogeneous objects in the entire universe, really, because there's only one shape that you're going to get a globular cluster in, and that's globular. So unlike galaxies where you've got spirals and ellipticals and irregulars and peculiars and all those great things, when you look at a globular cluster on a chart and then you go track it down in the sky, you kind of know to an extent what to look for. And these are all very densely packed agglomerations, really, of stars from 10,000 to about 10 million stars. In fact, the largest ones in the universe that we know of could have as many as 10 million stars in them. So in a lot of ways, they're like miniature galaxies on their own. And these are very old stars for the most part. A lot of what we know or knew about globular clusters has changed in the last 30 years. So there's really some interesting things to add to this. Most of the globular clusters in the Milky Way, there's about 160 of them that we know of, with more being discovered every couple of years. In fact, we just had the very first visual sighting of a globular cluster called Patrick 99 that was discovered about 15 years ago. And we just had the first visual sighting of it this year by a guy in California. So they're discovering these clusters that have been obscured by both being really, really far from us and along the plane of the Milky Way, where there's all the dust and organic molecules floating around that kind of block the view of a lot of these that are along the plane of the Milky Way. Again, they range from about 10 to 50,000 light years from us, from the majority, the closest one being M4 in Scorpius, which is about 7,200 light years, and the farthest one in the Milky Way being Arp Majore 1, which is 400,000 light years away from us, which is 4 times the diameter of the Milky Way itself. And yet it's still a part of our galaxy. Globular clusters range from about tens to maybe 175 light years. That's Omega Centauri, which is the biggest one in our galaxy that we know of. Obviously, in other galaxies, we don't know for sure, but in our galaxy, 175 light years is the biggest one. And we're going to see Omega Centauri show up repeatedly because of its extreme size and density. And the majority of globular clusters range about 1 star per cubic light year. So when you think of the nearest star to us being a little over 4 light years away, so we're looking at about 4 times as dense. In the average part of the cluster, in the core, there might be as many as 3 or 4 stars per cubic light year, which is pretty close for stars to be ranging around each other. And we'll talk about the proper motions in clusters as well. But when we talk about globular clusters, we're also contrasting them with the other kind of clusters in our galaxy, which are the open or galactic clusters. And you'll still see the term galactic cluster used. These two kinds of clusters have very, very different physical characteristics. You can tell just by a glance at pictures of 2 fairly average specimens that, yeah, they're made up of stars, but there's a lot of difference between the 2 of them. Open clusters, which are considerably more common than globular clusters, don't have a specific shape. You'll see all sorts of shapes. And in fact, if you look at them in a telescope, you're going to find yourself drawing your own patterns in them. They're smaller than globular clusters. Again, the smallest globulars are about 10 light years across. Open clusters generally are considerably smaller than that. Open clusters contain population 1 stars. Now, there are 3 populations of stars in a galaxy, and therefore 3 kinds in the universe. Our sun is a population 1 star. Population 3 stars don't actually exist anymore. They're kind of a hypothetical, and they help explain why there are heavy elements in the universe to begin with. Population 1 stars are called metal rich, and to astronomers, basically, metals are anything heavier than helium. So oxygen is a metal, carbon is a metal, basically anything beyond the first 2 elements on the periodic table are considered metals. And those are created in the nuclear fusion that's the process by which stars shine. Open clusters generally are comprised of younger stars, many of them newly born, as we see in the Orion Nebula. The trapezium in the Orion Nebula is going to be an open cluster, if it's not already considered one. The stars largely form at the same time in an open cluster. It used to be thought that happened with globular clusters too, but now we're starting to see that that's not necessarily the case. And again, this goes back to open clusters forming from a nebulous cloud of hydrogen gas and dust and sometimes organic molecules that condense to form a group or a batch of stars. Open clusters reside in the plane of the galaxy for the most part. So when you want to look for open clusters of stars with your telescope, you're going to look in summer and winter when you can see the band of the Milky Way, because that's where they tend to be located, because they form from this gas and dust, and that gas and dust resides in the arms of the galaxy too. Open clusters gradually disperse as the stars age and their radiation repels each other. They eat up the gas that they're formed from, and they tend to spread out in the galaxy. And in fact, the sun was formed in a cluster like this, of course, and they have recently found one of the stars that they believe formed in the cluster that the sun formed in, and it's actually pretty far from here. As the galaxy rotates and the stars get moved around like in a whirlpool, the open clusters tend to get caught up in that and mixed around. And open clusters, again, that origin from gas and dust is the only way that we know that open clusters form and young stars form. Now, globular clusters, get here, globular clusters, always globular or spherical in shape. They generally are larger. They consist of population 2 stars, which are older stars that have very few metallic elements. Again, anything other than hydrogen and helium. They're generally older stars, although as we'll see, that's not always the case. Globular clusters can contain multiple generations of stars, and this is a fact that's become apparent in the last 30 years. So this is still fairly new and fairly inadequately researched. Globular clusters reside in the halo of the galaxy, not necessarily in the plane of the galaxy where we see the open clusters, or they reside in the nuclear bulge of the galaxy around the center, the hub of the galaxy where everything's happening. They're bound together by gravity. They don't disperse except in unusual circumstances that we'll talk about later. And we know that there are at least 2 ways that a galaxy acquires globular clusters. And there's actually even now a third that goes back to some of the things that we've learned in the last 30 years that we'll talk about. And I can hear eyes rolling already from some of the people that have done a lot of astronomy reading. It's like, oh God, not the Hertzsprung-Russell diagram. But unfortunately, I have to talk about it a little bit so that we can kind of get into a little bit of the science. I'll try not to make it too in-depth. I once gave an entire talk on this diagram and bored the crap out of a lot of people. So I'll try to stay away from that. But the Hertzsprung-Russell diagram was developed in the 1920s to help understand the nature of stars and find out how to categorize stars. So in the case of this diagram, we have stars that are plotted by luminosity, with one being the luminosity of the sun, or the solar luminosity. And this luminosity is based on absolute magnitude, which is how bright a star is if you moved it to a distance of 10 parsecs. So you're eliminating distance this way and judging how bright or faint a star is. We're putting them all at the same distance and saying this one's brighter than this one. Along the bottom of the diagram, we have the star's temperatures in kelvins. So this particular version of the Hertzsprung-Russell diagram is measuring stars based on luminosity versus temperature. There are kinds of this diagram that are sometimes called color magnitude diagrams that have very similar characteristics, but those are specifically used to plot stars and clusters, and we'll look at those in a little bit. When we plot stars in our galaxy on this diagram, we see how they are categorized and how the majority of them fall along this strip, which is called the main sequence. And that's going to be important later on. Our sun is right here. And we have the red giants over here, the blue giants here, white dwarfs down here. And this particular version of the HR diagram also includes spectral class, you know, the "oh, be a fine girl, kiss me," or "oh, be a fine guy, kiss me," that they give you to learn the spectral types of stars in science classes. And those correlate very strongly with temperatures. So they run the temperatures down here along the bottom, and they've also got the spectral classes along with them. So you can see stars of the O5 type are burning about 30,000 Kelvin, all the way down to M5 at about 2,500 Kelvin. Most stars spend the majority of their life along this strip, and then as they age or die, they wind up evolving off of it, usually up in this direction. The bluer ones kind of evolve into blue supergiants there. Now, if we use a diagram like this to plot a globular cluster, we notice a lot of things here. This part here is the main sequence that we saw in the previous. This is where these stars lie on this diagram, or down along here. This is color coded by different actual clusters, not by star colors as much. The place that a star falls on the spectral class line tells you its color, but not the color of the dots used to represent it. So we've got a whole bunch of globular clusters plotted here. This part is a very important part of the diagram because it shows where the stars move off of the main sequence. And it's at that point that we can start counting the percentage that are off of the main sequence, off of this strip here. And the proportion of those off of the main sequence tells us how old a globular cluster is, because stars age and move off of the main sequence. So the more you've got up here, the more are no longer part of this strip that is kind of a standard age strip for stars. So as they move on up, they're getting farther and farther from that and making the cluster, or identifying it as being older. We're going to look at some of these other classes of stars here a little bit later, because these are fairly recent discoveries, and they're kind of important when you're talking about globular clusters. Now, these are comparisons of the HR diagrams, the color magnitude diagrams specifically, between open clusters and globular clusters. And again, we're using color here, indicating, in this case, I don't know why they use two different scales for these, because it's from the same data source. This is from the Gaia survey that was just compiled. And with the globular clusters, they're judging stars based on the amount of metallicity in them, the amount of elements that are heavy beyond helium. And here they're looking at the actual age of the clusters. So the stars here are the older ones, and they kind of trace out specific clusters of stars. I don't know why it's doing that, and it's really annoying. So sorry about that. So you can see that when you plot the stars of these two types of clusters, that they have very different appearances. I mentioned these other two groups here. This group here is a fairly recent discovery. These are called blue stragglers. And blue stragglers are interesting because they shouldn't exist in clusters. Globular clusters should not have blue stars in them. because they're made up primarily of old population 2 stars, and blue stars don't generally live that long. But in recent years, and in part because of Hubble, and hopefully in part because of James Webb, as we get data from it, now we know 2 ways that you can create new stars in a globular cluster, which was long thought to not happen. And in the first way, the collision model, obviously by the name you can tell what happens. You get two stars colliding, usually low mass stars, so not the red giants as much as the red dwarfs and such. And their collisions, as they merge together, form a new star that is excessively heated. It becomes a red giant and then shrinks and settles down as a very hot, smaller star, a blue straggler. The other method is a little less dramatic, but basically creates the same thing. And apparently there's evidence for both of these things happening in globular clusters that we've been examining with Hubble so far. So they've discovered these blue stragglers, which were long thought to not actually exist. They were theoretical, and even then a lot of people said, no, that theory is ridiculous. Another factor in globular clusters that separates them from other clusters is that a lot of globular clusters have black holes at the center of them. And they notice by taking photographs over long periods of time that certain globular clusters have the stars moving in tracks around the center of the cluster, as opposed to kind of randomly moving through the outer halo of the cluster. And by examining those with X-rays through radio telescopes, they've also determined the signatures of black holes in those clusters. So in a globular cluster, you might have 2 different forms of motion depending on the type of cluster. Here's a close-up look at the core of Omega Centauri, and already you can see that there are blue stars in there. And Omega Centauri is what's called a non-collapsed globular. And this idea of collapsed versus non-collapsed has a little bit to do with the black holes that may be at the center, but it has more to do even with a visual impression. And this is something where visual astronomy has still proven to be really useful in understanding these, and has not totally been superseded by theoretical science and mathematical modeling. The tightness of the core of a globular cluster can give you a hint as to what kind it is. And we'll talk about that later too, when we start classifying them visually. In a globular cluster where there's been a core collapse, frequently with an interior black hole, you might find stars as tightly packed as the distance between the sun and Pluto. So on the range of 4 to 5 billion miles, as opposed to light years. So these can be incredibly tightly packed. And in those cases, you might find more blue stragglers because you have more stars in a given area that can merge or collide with each other. We know that the more massive stars in the middle of the cluster might tend to be the ones that are, or the more massive stars in the cluster might be the ones that tend to get pulled into the middle. Things like white dwarfs, neutron stars, things that are not as easily moved away from the center by the heat and the radiation from the other stars. They have enough mass that once they get to the center, they kind of tend to stay there. Now, the resolution that we see here in Omega Centauri kind of indicates, and a more wide angle picture certainly does, Omega Centauri is a non-collapsed globular. So the central concentration is not nearly as intense as it will be in some of the other ones that we look at. This bottom picture shows us the motions of the stars in the little inset here. Each of the little dots on these tracks, and you'll see them more plainly in some than in others, marks a movement of 30 years that they've been able to track back to a certain extent. And from the point where they started getting photographs beyond or before that, they extrapolated a lot of this. So these tracks basically cover, there's 20 dots in each, so they cover about 600 years of proper motion within the middle of this cluster. And we can kind of see that they're going every which way. So we also know from that there's less likelihood of there being a black hole at the center.
Hey, Andy,
Yeah.
Dan's got a question.
Okay.
Sorry, and I promise I'll keep it quick. So if there was a sun mass and brightness star where Pluto is now, how bright would it be to us?
Oh boy, that's
I mean, I'm just curious about the actual proximity. You know what and I guess the follow-up to that is, I'm guessing there are not planetoids around stars in globular clusters, right?
Right. That's very true. And I'll talk about that in a little bit, but that's true in large part because they have there's so few metals in the clusters to form planets from.
Okay.
But there are some that do have it, maybe enough metals in it. We'll talk about it later.
Okay. Thanks, Andy.
But it's rare that there's the possibility of that. As to the first question, we'd probably have to use the inverse square law and assume two stars like, the sun and another one just like it, and then use the inverse square law to figure out how bright it would be. I don't have the math skills for that off the top of my head. So
I'm just wondering if it would look like Venus or if it would look like a small sun or the moon, or
I think it would be considerably brighter than Venus, but again, that's something that we could figure out later on. I'm sure if Bob Anderson is listening, he's probably working on it already.
I got him beat. I just now calculated it out.
Yeah.
It would be 1/1600th as bright as the sun, which is still going to be really, really bright, much brighter than Venus.
Yep.
Okay. The sun being magnitude -26, but that's also on a logarithmic scale, and I know there's no way I can figure that out.
That's right. I'll work on that while you're finishing your talk here.
Okay.
Just all right. Thank you. Not a problem.
Okay. Yeah.
This NASA page says 300 times as bright as the full moon.
Wow.
Okay.
Okay. So they're close by. I mean,
Yeah.
that's okay.
Yeah. Wow. We wouldn't be getting many clear nights in those instances. We'd be lucky to have a normal day when they eclipsed each other. So anyway, until recently, like I said, it was long thought that all globular clusters had the same basic origin. They all accreted along with the galaxies, a little bit ahead of the galaxies. In fact, they were considered to be as old or older than the galaxies that fill up the universe. Now that we've got new theories about how they can form, and we have refinements on the data about individual stars and globular clusters and just massive quantities of data, we've been able to refine that a little bit. And now it seems likely that globular clusters largely originated at the same time or just after the galaxies formed. And they formed by the accretion of hydrogen gas the same way the galaxies did. And with the older population 3 stars, the hypothetical population 3 stars that I mentioned way at the beginning, those were what introduced the metals into the universe that when those stars died, the metal, the metallic elements from lithium on, all were scattered through the universe by the deaths of those original population 3 stars that they've kind of hypothesized, I think, to help explain where the metals came from. Also in the universe and in quantities around any large galaxy are dwarf galaxies. These were discovered back in the late 70s with this particular one, the Fornax dwarf galaxy and the Sculptor dwarf galaxy being some of the first ones discovered. Every large galaxy has its own retinue of these little galaxies, and it's by swallowing them up, and we'll talk about that in a bit too, that we wind up adding to the currently existing galaxies. They get cannibalized, and this cannibalization helps to give us more globular clusters. We see 4 of them in this picture of the Fornax dwarf. One of the globular clusters in the Fornax dwarf is so much brighter than the dwarf itself that it has an NGC number, and yet the dwarf wasn't discovered until the late 70s. So we can see in the pictures of these 4 globular clusters that are part of the Fornax dwarf galaxy, you can see really clearly what we talk about by collapsed and non-core collapsed clusters. These 2 obviously being non-collapsed, and these 2 where the cores are very tight and the stars are more densely packed in the center. So 2 of the more recently discovered dwarf galaxies around the Milky Way were discovered in part by following the streams of stars and material that they left as they've passed through the Milky Way. So the gravitational interaction with the Milky Way is cannibalizing the stars and the clusters and other objects in these galaxies and absorbing them into the Milky Way. These 2, again, being 2 of the more recent ones. And in the case of the Sagittarius dwarf, it has been a very solid donor of material to the Milky Way. And we have here, yes, it's going to play, kind of a short video of this cannibalization of a dwarf galaxy as it goes through the disk of the Milky Way and winds up losing much of its identity and becoming what's basically called a tidal stream. At some point, it's just no longer considered a galaxy. It's just this stream of material. There's no real coherence to it anymore. And along with those stars and that other material, well, before I get to that, actually, we now have tracks. This is obviously not a photograph, but these are illustrations of some of the tracks that are left by dwarf galaxies in their passage through the Milky Way. Each of them plotted here in a different color to keep the tracks straight. I actually have a really cool website at the end that I'll show you that allows you to do a lot of digging into this interactively. The most prominent of these dwarf galaxies in terms of giving us material and such, like I said, is the Sagittarius dwarf elliptical galaxy. There's also a Sagittarius dwarf irregular galaxy that's not the same thing. This galaxy or its remains are about 10,000 light years and about 50,000 light years from the center of our galaxy. It's had a number of passes through the disk of our galaxy, and each time losing a fair amount of material. And they are able to trace this track back through, I think it said 8 billion years ago, so half the age of the universe, certainly, that they're able to determine how many passes this has made through the Milky Way. And that's important because as it's done that, it has given us a bunch of globular clusters, which are some of the first things that a dwarf galaxy loses when things get pulled away from it, because they're solid and they tend to be pulled away from the dwarf galaxy pretty easily in a gravitational tug of war. These are only 4 of the ones that were given to us by the Sagittarius dwarf elliptical galaxy. This one's M54, so fairly easy to find one. This is Terzan 7, Terzan 8, and ARP 2. These two don't look much like globular clusters because they're extremely distant from us. They're on the other side of the galaxy. And as we see them, we're looking through the plane of the galaxy, through all the gas and dust that have coalesced into the plane of the galaxy. This is something I'm hoping that Webb gets some really good images of, because it sees through that gas and dust via the infrared. So we might get some good looks at some of these globular clusters and probably find a bunch more of them that we can't see at all. And now we come back once again to Omega Centauri, because it's really such an exception in so many different ways. But Omega Centauri raises another question about the origins of globular clusters. In fact, gives us an entire third theory. Okay, we get that a lot of them have coalesced around the Milky Way when the Milky Way formed, and we get that as the Milky Way interacts with its dwarf galaxies and cannibalizes them, that it absorbs those globular clusters from those galaxies. But now we get a third idea, which is the most recent, and that's the idea that some of these really large globular clusters are in fact the cores of dwarf galaxies, all that remain of the galaxies after a certain amount of material and stars and other things have been ripped away from them by larger galaxies. And one of the reasons that we think this about Omega Centauri, and also a cluster called G1 or Mayall 2, it's the same cluster in the Andromeda galaxy, which is the nearest large galaxy, and it's one of its globular clusters that we can actually see with backyard telescopes. It's so bright and so big. We know that these globular clusters contain multiple populations of stars that blue stragglers don't account for. So that would be explainable by the fact that this is what's left of an entire galaxy that has kind of condensed upon itself through gravity. It's got these multiple populations of stars just like a regular galaxy would, and like the dwarf galaxies do. They have younger and older stars, some of which are metal heavy and some which aren't. And about a third of the globular clusters in a given large spiral galaxy may be of this type. Omega Centauri is the most obvious example because it's been really well studied, and it's also nearby. It's easy to do that study. Up to as many as 60% of the Andromeda galaxy's globular clusters may be galaxies of this type. And again, hopefully Webb will help shed some light on that. Here again, we see blue and red stars in the core of Omega Centauri. So there are both populations there. As Dan said before, or had asked before about planetary systems, you know, when you've got so many stars packed together in the center of a cluster, it's really unlikely, even if there's enough metal-rich material there, that there's going to be anything that can condense into a planet, certainly a rocky planet. because the gravity and the interaction of these stars with each other is going to basically prevent anything from accreting or condensing. A planet that orbited the same distance from the sun or from its star as we do from the sun, so 1 astronomical unit, anywhere in the middle of a globular cluster, certainly beyond the very most distant stars in the cluster, any planet that orbited one of those stars is likely only going to have a lifespan of a couple 100 million years or so, which is basically only enough to condense and then be torn up. So anything that was planetary in nature that was within one of these clusters isn't going to make it very long. So we think back to our wonderful color magnitude diagram. You guys thought you were done with the science. We're almost done with the science, I promise. But if we look back at that, we found a section called the RR Lyrae stars. And there was a weird gap in the diagram where most of those should have been. There were a few there, but a lot of those were missing. And the RR Lyrae stars, as the name suggests, if you do a lot of reading about star types, are a type of star that varies in brightness, which also helps explain why they don't show up on the Hertzsprung-Russell diagram. And as you can see from this image, there are stars in this cluster that vary in brightness by frames, and the frames were taken a day or so apart. There's only a few of them in here, but you can see that there are stars varying in brightness here. And many of these are the RR Lyrae type of star. And here we can see that the RR Lyrae star changes brightness by an order of 1 magnitude in just over 13 hours. About 13 and a half hours. And this is actually going to become really important when we start talking about the development of theories of the universe here in a minute. But the brightnesses of these stars fade and brighten over 13 and a half hours. And many of these stars are found in globular clusters. This is also an image that shows a number of variable stars in M3, Messier 3. Obviously, some of these are brightening because of the differences in the various frames. This image was actually compiled in Portland by a guy who was doing amateur astronomy from downtown Portland. He got this set of images of this cluster. And so some nights the seeing was a little bit better. And so some of that variation is because of the photography itself, but you also see the variations of some of these stars. And there are more than one type, certainly, of varying stars, variable stars, in this particular cluster, and probably in most of them too. And here are light curves for 2 of these. This is an RR Lyrae type star. And the reason this is important, I've got one more slide before I can tell you why it's important. So here again, this is a diagram of the cluster Messier 5, M5, which is one I'm sure we'll be looking at Dexter on Saturday night, hint, hint. But here's where we find these stars. And you notice there's a long string of stars here. These are very, very old stars in here. But we notice that this one is not really very coherent. And that's in part because the stars vary in brightness. And so they would show up in a long strip here. And some of them just don't make it on because this axis of the diagram is in luminosity. And here again, not entirely sure why I put another slide of this in here. But the reason the RR Lyrae stars are important, and I really wanted to do a Vince McMahon style introduction to this, in this corner, kind of, we have Harlow Killer Shapley, and in this corner over here we have Bear, the monster Curtis. But in the 1920s, and specifically April 26th of 1920 at the Smithsonian Institute, there was what was called the Great Debate. And at that time, we knew very little about the actual structure of the universe, and the size of the universe as well. And despite having several hundred years of astronomical observations behind it, we were still kind of grasping at straws as to what the size and shape and structure of the universe was. And these two guys, the young upstart Harlow Shapley and the old guard Bear Curtis, over here with the glasses, kind of got together and held a debate for the astronomical community and the public at large. And each of them had their own ideas about the shape of the galaxies and the universe. To Harlow Shapley, over here, the new guy on the scene, he had taken a lot of observational data and had decided that the Milky Way was the universe. The entirety of the universe was this thing that we called the Milky Way. And he believed that it was twice the size that it is, which still makes a really small universe, because we're talking there about 250,000 light years across if it's double the size. And he believed that what they called the spiral nebulae, which were spiral galaxies, of course, were actually objects inside the Milky Way, and were in fact places where stars were collapsing and where star and planetary systems were forming. They called galaxies nebulae all the way up until the 1960s, in fact, which is a lot of fun if you're reading old astronomy books to keep those straight. Now, Curtis believed that the Milky Way was only about a quarter of its present size, but that the other spiral nebulae were independent objects. They were outside the Milky Way. Shapley had at his disposal the RR Lyrae stars, which he had been using, observing them in globular clusters, and said, you know, this is that exact same type of star based on how dim it gets, how great the fluctuation in its brightness is, and how fast it happens. It's the exact same kind of thing, only a lot farther away. So using our friend the inverse square law, which we were just talking about a little bit ago, kind of randomly, and it comes up again because it's really important with this, we find, or Shapley found, that he could measure the distance to the globular clusters by determining how far away those RR Lyrae stars were based on how much dimmer they were than the ones that we could see close by. And using the inverse square law, okay, an object twice as far away gives us a quarter of the light. An object three times as far away gives us a ninth of the light, and so on. So that's the inverse square law. And so doing so, he was able to somewhat accurately place the globular clusters in direction and distance from us. And he found that the globular clusters form kind of a shell around the galaxy. There's a lot of them concentrated in around the nuclear section of the galaxy, and a lot more of them concentrated around the outer edge. So who won the debate? Well, they both kind of did, because Curtis was correct in the fact that the galaxies, or the spiral nebulae, were external to our galaxy. But Shapley was more correct in being able to determine the distance to the globular clusters fairly accurately, and he was closer to the Milky Way's actual size than Curtis was. So they call it the Great Debate, and you can even probably look for it on Wikipedia. Just type Great Debate, and that's what'll come up. Although it's kind of a fizzle, really, because both guys were right and both guys were wrong. And later data has kind of superseded both of them. So this is the end of the sciencey portion of the presentation. And here we have more globular clusters than we'll ever know in our galaxy. This is the galaxy M87 in the heart of part of the Virgo supercluster. And it has cannibalized lots and lots of galaxies, some of them really big. And as you look at this image, you'll see all these little dots around it. Those are individual globular clusters. We have, that we know of, 160 globular clusters. M87 has at least 10,000. And it's a much, much more massive galaxy than ours is. So in a way, it's kind of a globular cluster of globular clusters, if you think about it that way. And this is important to us because this is going to be the fate of all galaxies. They're going to wind up coalescing into these giant super galaxies, which will then unfortunately age and dissipate, and there goes the universe. See you later. So we're going to end on that note and go to...
You've got a couple questions if you want to answer.
Sure. This is the best time.
Chat.
Yeah.
Can you see chat?
I can see chat, but we love the science. Thank you. Thank you. Okay. Why don't we see lensing of the stars behind globular clusters? I suspect that's because there's not enough massive objects behind them, or in front of them to lens them. Or are you're saying the globular cluster being the lens?
Yeah, I was just curious. I mean, I because the line below that I mentioned our own sun was able to lens the light from a distant star, and that was that observation during eclipse is one of the earliest proofs of relativity. So I was wondering why we don't see lensing all over the place around globulars, just of the stars behind them.
I honestly don't know. I suspect it's probably because of a combination of mass and distance.
Yeah. Or it's just not visually obvious the way that you get with a galaxy. It's not to be, noticeable.
Maybe the things behind them aren't near enough, or I don't know, for the lensing to
kind of a Bernie Bob question. Something that came up while you were talking about them.
Jerry? I have a theory about this, actually. My theory is that the globular cluster is too dispersed. There might be lensing going on, but it would be lensing right near the core. And so the cluster itself is probably hiding any lensing effect that you would see because there's so many stars in front of whatever you'd be lensing.
Interesting. Okay.
Yeah. Okay. Well, that's a better explanation than I was coming up with. So yeah. Is there a particular cluster where the RR Lyrae stars were used to win the debate? I think that because he created this notion of the halo of globular clusters, and in a lot of ways created the idea of the halo of a galaxy by these things creating or being a part of this fairly invisible halo to us of material around our galaxy, beyond which you are in intergalactic space. So the globular clusters are kind of like marker buoys. Beyond here, you're on your own, kind of. I think because of that, he had to have used quite a few globular clusters to get his data. So as far as a specific one or a number of them. I think he probably used as many globulars as were known at the time, which is basically anything in the NGC, really, the NGC and the IC catalogs. He probably used as many of those as he could get data for. So I don't know that there was a specific one or a small set that he used. I think he used basically anything he could get his hands on for data.
Hey, Andy,
Yeah.
I got a quick question.
Mm-hmm.
So when you were describing how the globulars, when they're starting to coalesce and they go around our universe,
Mm-hmm.
if that happened while in our time, what would that look like in the sky? Would that look like planets cruising by slowly, or would that look like shooting stars, or would it just wipe us out?
Oh boy, that's a good question.
I just was wondering what it would visibly look. Would it look like 10,000 suns in our sky? I mean,
When a globular coalesced,
yeah, when it would come right through our arm of the Milky Way.
I suspect that at that point it would be somewhere between looking like kind of a lumpy elliptical galaxy where the stars hadn't quite formed yet, or I guess it depends on the stage of evolution. At the stage at which the cluster had condensed, you might have a set of stars that condensed before the others in the cluster. I don't know.
Yeah,
That's a good question. I never thought about that one.
just trying to fantasize what that would look like in the night sky, or even maybe in the daylight sky. You might see it, because if these are stars coming through,
Right. Right. I think it was
talk about global warming, huh?
yeah. Isaac Asimov wrote the story Nightfall about people who are a civilization on a planet inside a star cluster, and how they kind of lost their minds when the last of the stars went into an eclipse because they'd never seen night before. I think if that was to happen to us, I think we would kind of be in that position. There would be so many stars in the sky at a given time that there wouldn't really truly be a night, especially if we were anywhere, near the interior of the cluster.
Yeah, I'm sorry to distract you. I just thought of that as a question. It's like when you were talking about it, and it's like, wow.
Yeah, there are a lot of artist depictions of what a globular cluster in someone's sky close up would look like. I actually have one at the end here.
Oh, cool.
But
Good.
it's
Thank
not
you.
really accurate, let's say.
Yeah, that's
the
cool.
majority of them probably aren't.
Thank you.
Yeah.
And that's the same question as my Pluto question. Really, I'm just going to how bright these guys would be at distances that you're describing.
Mm-hmm.
All right. Thanks so much.
Okay, so for the observational portion, and again, if anybody's got questions, this is an intermission of a sort, so we'll have time afterwards for some more. But let me get up here, and why isn't it letting me share? There we go. And we're gonna slideshow part 2. This is the observational part. We're a lot more than halfway along. So this is, I think, the fun part, because this is about getting out and actually looking at the darn things instead of sitting here talking about all the numbers and such, although the theory is great too. It's really commonly said, and I've been a part of this discussion myself, that all globulars look kind of alike in the eyepiece. And yeah, that's sort of true and sort of not. They each have their own character. These are all sketches done by the same guy of a number of globulars and with the same telescope. And you can kind of see how even though they're all round blobs of stars, they each have their own individual character to them. When you look at globular clusters in an eyepiece, you may find them with a low power eyepiece, but because the majority of them have a high surface brightness, you can use a lot of magnification on these things and basically blow it up so that the cluster fills the entire eyepiece. So if the night sky is really steady, if the seeing is good and you're looking at a globular cluster, just take it all the way up with the magnification that you've got. The the Astronomical League has a program where you can get a Pan certificate for observing 50 globular clusters and taking notes on them and sending them your notes, and they'll say, you know, that's a good set of notes on 50 globulars. So here's your certificate. Congratulations. I did that particular one. You get to pick any 50 globulars. I deliberately avoided all the easy ones like M13 because I'm just kind of weird like that. You know, M13 would be too easy. Let's do some of these other ones. But we talked earlier about how you can find, or how you find globular clusters mostly around the bulge, the nuclear bulge of the galaxy and out in the halo. And that's borne out in our sky really well. When we look at the winter Milky Way, we're looking out through a spiral arm out into intergalactic space. And so most of what you'll find along here is open clusters, and there are a very, very few globular clusters that can be found in winter. These are the only 4 that are really readily visible in a backyard telescope. There are a couple of other ones that are really faint, really difficult, and a lot of fun to look for if you're a masochist like I am. As we move away from the winter Milky Way, we start seeing a few more of them appear. These are globulars that are found in the springtime sky. That opening photograph where we had the 2 of them right next to each other, that's this pair right here. Very different types of clusters. But now as we advance into summer, on a week from Saturday, not long after sunset, we're going to be looking right at the densest part of the Milky Way down here in Sagittarius, and therefore looking at a cross-section of the galaxy where the majority of globular clusters are found. So this really is the time of year when you want to go doing your globular cluster marathon. There are more of these in the night sky now than any other time of year. And as these are some of the easiest objects to look at in terms of you can find them even from pretty near Eugene, even at the reservoir for our first quarter Friday, there are a lot of these visible. So even if you're in light polluted skies, you can see a lot of them. So this is the time to get out and do it. And then a couple months from now, we're back with only a very few left to look at in the fall sky. Most of them will have set by the same time of night. This one here just happens to be the brightest one in the Andromeda galaxy, so we don't even really count that one because it's not part of our galaxy, but we've got a fairly limited number of them here. Now for the not quite as fun part, if you're doing the Astronomical League's Globular Cluster program, because they tell you, oh, you have to try to estimate the concentration class. And this goes along with our core collapsed clusters versus non-core collapsed clusters. So the ones at the low end of the scale, number 1, being the most concentrated kind of cluster, to being class 12, the most diffuse and unconcentrated types. Now, these photographs don't nearly do this justice because a lot of these look very, very similar. And in a lot of cases, they don't even look like they're in the right order. So as we go from most concentrated to least concentrated, it actually helps to be looking at these in a telescope, because photography tends to overexpose the center of these. So you never get a really good look of how concentrated they are. The centers almost always look fairly similar. And as we do a really quick run through of what they kind of look like, more sketches. We're just going to kind of whip through all the classes here from 1 to 12. And the one on the left-hand side of your screen is the lower number, the class 1 versus class 2. And you can see that, again, versus photographs, these all have their own character. So regardless of the fact that they're all basically the same thing, and the fact that they, have the same shape, they do look different in the eyepiece. And I got to say that sketch of M5 over here is phenomenally good, because you can trace out the little arms to it in the sketch that you get in the eyepiece that make it so distinctive. You can look at that one and say, oh, that's M5. I don't even need to know which one it actually is, because that's exactly what it is. It's the only one that looks like that. Now we're getting toward the more loose ones, M22. And on down to class 12, which doesn't even necessarily look like that particular cluster, which is a lot fainter than that. But there you can see there's almost no central core to these. They're just a blob of stars there. So these are very much the non-core collapsed globulars. If you really want to get masochistic and hate yourself, you can start looking for some of the really distant globular clusters in our galaxy, which don't even look like much of anything at all, like these guys here. This particular one here is one that was discovered only 15 years ago, and I wish my computer would stop doing that. These all four are very distant and or seen along the plane of the galaxy where the obscuring gas and dust are. Which one of these is, okay, this one, Art Madore 1, which we talked about at the very beginning because it's the most distant globular cluster in our galaxy. Using the magic of Sky Safari, we can actually see how distant this globular cluster is in comparison to the Milky Way. It's actually 4 times as distant as the Milky Way is across, roughly. So not just in this dimension, but here too. So it's actually farther than it looks in this image. So why is it still part of our galaxy? Well, it kind of barely is. And as they do more studies on it, they may find that, hey, this thing is actually in intergalactic space. It's no longer under the gravitational influence of our galaxy. So all the more reason to look at it. So you can say, I'm one of the few people that's ever seen this thing. Because why wouldn't you want to be one of the few people to see something? Here's a sketch of that. This one here, over here. The guy actually wasn't even sure he saw it. And this is one of the best sketching guys in amateur astronomy. So this is actually where he sketched it. You might not even be able to see it, but right there's a really faint spot in the sketch. And he says, well, I saw something enough to draw it, so maybe I really did see it, or maybe it was just a floater that didn't get out of the way. So now you're looking at globular clusters that don't even look like clusters. They don't look like much of anything. These are 2 sketches that I did way back of 2 other ones that are really far. This is Tarzan 7, which is one of the ones that was torn off of the Sagittarius dwarf elliptical galaxy. Doesn't look like much, but hey, this was a 12.5-inch telescope and not from a particularly good sky. So from where we are, you could probably wind up nailing this one if we were about 10 degrees farther south, because this is below the bowl of Sagittarius. This one, I know a couple of us have seen. This is Palomar 12 in Capricornus. That's really annoying. So I know a couple of, I'm going to kill this computer in a second. Oh. And I promise you can see some of these globular clusters with telescopes like the EAS 18-inch telescope, which is just waiting for somebody to borrow it.
Yeah.
If you're courageous, if you are men and women of valor, you too can use the 18-inch Tony Danduran, Frank Zapansky telescope. Please get it out of my garage. Look for faint globular clusters. So beyond trying to get the 18-inch scope out of my garage, we also have globular clusters in other galaxies to look at. And these don't always take really, really big telescopes. In fact, we talked about one in the Andromeda Galaxy, which we'll look at in a minute, but there's a whole lot of them in the Andromeda Galaxy. And in fact, this is from the 1960s, and I guarantee they've found dozens more since then. There are people on cloudy nights and elsewhere that have gone out and made this the entire focus of their evening, was finding these little faint star-like globular clusters in the Andromeda Galaxy. Not really my cup of tea, but it might be yours. And you can find them with the 18-inch telescope. The brightest of those, which wasn't even on this picture because it's so far away from the Andromeda Galaxy, is Mayall 2, also known as G1. A little finder chart for finding it. Again, a bit of masochism involved, but it's not really that bad. And it's this little tiny thing right here in the middle, flanked by two stars on the edge that make it look like Mickey Mouse.
It
It really does.
I will point out that I can see that in a 10-inch telescope. So if you've got a 10-inch or greater, you can do it too.
Yep. Yep. And I know because Jerry has showed it to me. I've never actually had the moments of patience required to track it down. But yeah. So, hey, not just looking at globular clusters, but stuff in another galaxy. How cool is that? You can do that from any of our observing sites. But why stop there? Why not look at other galaxies that are satellites of the Milky Way, like the Large Magellanic Cloud, which has all of these little things in it labeled, many of which are globular clusters, some of which are open clusters, and a galaxy that you have to go down to the southern hemisphere to observe. But hey, why wouldn't you go to the southern hemisphere and haul your telescope with you? Because if you don't, you're crazy. Because that's where a lot of the fun stuff is. Globular clusters in the Large and Small Magellanic Clouds. Don't miss them. This is a galaxy, another satellite of the Milky Way called Wolf-Lundmark-Mayat, found in the constellation Cetus. Yes, it's visible barely. It's like somebody put a thumbprint on your eyepiece, but it too has a globular cluster right here that is readily visible in a 14 to 20-inch telescope, like the EAS 18-inch telescope currently occupying space in my garage. You just look for the two objects on one side of it that are so far apart, and you say, that one to the south, that's a globular cluster. Wow. Spent a lot of time looking for it, and it doesn't look like much. But a globular cluster in another galaxy, why wouldn't you look for it? And then you can get really crazy. And you can look for globular clusters in satellites of Andromeda, because why wouldn't you? There's all sorts of them out there. This is somebody's bucket list. I know it. And since we're done talking about globulars in our Milky Way, and I don't have anything else to add, this is a very fantasy-oriented rendition of the view from a planet orbiting in the distant reaches of a globular cluster with only one really bright star in the sky. I'm not sure I buy it, but
So kind of like the scenario I had, maybe.
yes,
Yeah.
very much so. Only I don't think you'd get night that dark.
Oh, I want to see this.
Yeah. But hey, it's casting shadows.
How cool is that?
Yeah. There are actually quite a lot of pictures like this on the internet, guys doing computer art of globular clusters in the sky and things like that. But this was one of the only ones that I thought was even remotely realistic enough to throw in here. And it's just kind of cool.
It's really
So
How about the Triangulum galaxy? It's loaded with NGC objects and little blobs. It seems
yes,
like
it is.
you could much more readily find than, you know, some of these faint fuzzies you're describing.
Yeah. I've cataloged a bunch of NGC and IC and other objects in M33, but I didn't actually have a chart for the globular clusters.
I see.
And I didn't have a good chart of that one. But yeah, there are a lot of them that you can see there in M33. There are a lot of them in other spirals, M74 in Pisces, which is considered the faintest of the Messier objects, actually has a couple that really, I want to say dedicated because that's the polite word, but I'm just going to say bonkers guys on the internet have observed.
Yeah.
Oh, I'm going to track down a globular cluster in M74.
Yeah, like club presidents that recommend we all run out and try to see Iapetus, you know.
Well, I tell you, if you don't have a 20-inch telescope, you need to catch up. You got to keep up with the Australopithecines.
At 18 at the least.
What's that?
An 18 at the least.
Yeah.
Right
There
there in
you
your
go.
and
I know where to find one.
I'm
Yeah.
happy.
When you,
Okay, you know, I deliver as
I was going to say, we'll deliver it. Or things sitting unused in the garage.
You know, you were talking about how they were calling it nebulae and not galaxies.
Mm-hmm.
So I grabbed my handy dandy 1956.
Yes. I love it.
It says right in here. There's satellite. Our galaxy resembles the Great Spiral Nebula M31 in Andromeda.
Yep.
So they were like hedging their bets there.
Yeah. And all the way up until the late 1960s, you'll find astronomy books that use the term galaxy and nebula interchangeably. I mean, here's another one, another classic. Oh, sorry.
There we go.
Field Book of the Skies by William T. Olcott, which is another one of those books that you read from the library when you're a kid.
Red Giants and White Dwarfs by Robert Jastrow.
Jastrow, yeah. Or Jastrov, I think it is. So, yeah. Anybody, anything else? I do agree with the suggestion that you have to stargaze socially, because that way, if you see something that's identifiable as a floater in your eye, you can have somebody else confirm that it's not there. I think that's really good advice.
I like it.
I remember reading somewhere that there was somebody that like mapped all these canals on Mars or something, and then it basically mapped the veins in his eyeball or something.
Yeah, that was Percival Lowell.
It was the first retina scan.
So the real question is, do you want to take somebody skeptical or somebody gullible out with you? It depends on whether you want a confirmation or not.
Well, in this club, we only want skeptical thinking. We want verifiable facts, not imagine. Oh, no, that's not true.
Verified observers.
I think you got to have both.
Yeah.
I think Carl Sagan was right. You got to have the imagination to go along with the analysis.
Some of each is good. Sometimes it is helpful to your self-esteem to have somebody tell you like, "Oh yeah, you found it. Good job, buddy."
Yep. Well, hey, if I see something really, really, really super faint, I'm gonna look around for somebody else to say, "Yeah, I see it."
Well, no. Also, it's critical. I thought I was looking at Stefan's quintet just a few nights ago, and I thought I was seeing the brightest of the galaxies and some kind of smudgy stuff around it. And Jerry came over and said, "No, you're next door, but you're actually looking at NGC XXX 123.
7331.
6331.
Yes, he's still got it.
C30. Which one is that?
It's Spiral Galaxy and Pegasus.
Yeah. So we just had to wander a couple degrees, to the west, and there it was. But oh my gosh, so much fainter, and probably not worth. I don't know. I mean, in a 20-inch scope, we're because what we were looking at were prospects for the upcoming star party that could resonate with web enthusiasts. But
right.
Pretty faint, and so I put myself in the shoes of a 12-year-old who'd waited in line for 30 minutes. and then I thought, I think we're going to stick with M13 and, ring.
Here's an idea.
That's one.
Show them C30 and say it's Stefan's quintet.
Yeah.
It's pretty close.
Robert, that's what I did. I called you over and said, look, check it out.
Yeah, you did that to me. You turned me into a little kid and
that's right.
Destroyed my hopes and dreams. I'm just finding out about it now.
Dan, I actually think that's one that after the crowds thin out, that's the time to do it.
Sure.
What?
Sure, I agree. Yeah. No, it was there when we did actually put the scope on it, and I've seen it at the dark site, but it was not.
Yeah.
Not
I actually saw that in my 4-inch Unitron refractor at Linslaw one night.
Really, Stefan's quintet?
Yeah, you and Kathy both helped me verify that's what it was.
Okay.
I remember that.
Yeah.
So we saw it in 80mm binoculars Tuesday night also. Just barely.
Yeah. As you would.
Saw is kind of like it was a little bit less black.
Yeah, there was something there for sure.
Yeah. Well, if you can see NGC 7331, the big bright one nearby, hey, take a look for the quintet.
Yep.
So there's no reason not to.
Super cool talk, Andy. Thank you.
That was great.
Thanks.
Thank you. I hope it wasn't
no, the time by.
As I was going back through it, it's like, oh geez, there's a whole lot of this I should have skipped.
No.
No. And I think I have a map of the globulars in the Andromeda Galaxy in a PDF form, if anybody wants to give it a shot.
Oh, nice.
Because I did that one night. I just spent the entire night tracking down globulars in the Andromeda Galaxy, and I pegged 7 or 8 of them.
Why don't you post that on the group?
What's that?
Why don't you post it up on the group?
Yeah, if I can find it, and if it is in fact in PDF form, I know I have a printout, and I must have gotten it from somewhere. So
that reminds me, actually, I do have one more thing I wanted to screen share here. I don't actually even know if it's going to work because it's interactive, but I can show you anyway. This website, which goes by the name armchairastronautics.blogspot.com, and is Milky Way Halo. You can all see this.
Yeah.
This is really cool because when I had the image up early on of the Milky Way with all the different colored tracks of dwarf galaxies and such that had been ripped apart, this allows you to see all of those. There's a set of labels here of the different streams of dwarf galaxies, and it identifies objects based on what they are by classification, where they are in our galaxy, the bulge, the disk, the older young halo, and you can zoom in and it will show you all of the objects and the tracks and basically the residue in a lot of ways of the passages of these dwarf galaxies. All the way up to the galactic pole. All the way down to the south galactic pole. You can zoom in.
Let's see.
Robert put the link in the chat, by the way.
Oh, good. Good. Yeah, I thought this was a really kind of a spectacular piece of cartography here to be able to do that.
So Andy, being the, I don't know, nerd you are, you left out some obvious things. I thought for sure you would talk about the propeller in M13 and some of the, the visual delights that are out there in the more familiar globulars. But I found it really fun to read about the propeller, and then even more fun to see it, and then even more fun than that to never be able to unsee it once I'd seen it. I've been staring at it for years, and then suddenly, I got to look at it, and just for fun. Will you throw that up? And I get it. People like to discuss it because there should not be dark lanes in globular clusters, and so it's probably just a trick of star placement in light. But
right,
I also kind of thought it was fun to read a whole lot of the pseudo. Well, there's some fairly scientific attempts at describing it.
Okay. That is something that I did miss. I didn't even think about that. Now I'm gonna do Google search here.
Stuff.
I have no idea what's gonna come up. So
Living dangerously.
I'm pretty sure you don't need the safe search turned on for M13 propeller, Boo.
Yeah, you never know.
Could be a position. Okay, anyway.
I've got a sketch of it here if you don't find a good one.
There it is. Well, there it is.
So, yeah, this is a feature.
Well, go up one so you can see what it looks like in the eyepiece. That's a reverse image, but it was present in the image just upstairs from there. No, you don't have to go back. Yeah,
this one here.
Sure. There.
Oh, yeah, there it is.
That's a little bit more what it looks like in the eyepiece.
Yeah, it's one of those things that does not show up in photographs except under certain circumstances. Let me see if there's an actual photograph that has it.
Actually, I didn't notice it until I looked at it with my intensifier. So it actually, there it is. Yeah.
Yeah, that's actually got it.
That's what it looks like in the, oh boy. Yeah. And yeah, there's a nice.
Here. Sure. This almost perfect 120 degree.
Yeah.
Divide your pie chart in thirds right there.
That's a fun thing to show, I think, at outreach events. Some people see it and some don't, but it's something that you kind of, once you see it, you can't unsee it.
Another thing that I like to show, because I'm that way, is the little galaxy next door to M13.
Right.
Yeah.
Oh yeah. Always overlooked.
Yeah. So when you've got M13 and you've got the two bright stars that flank it, not only is there a really faint one here. Oh, there we go. But you got this nice bright little galaxy down here that's actually really easy to see. So another one that's right nearby the larger object.
And there's the propeller.
I see the propeller here.
Yeah.
Right there. There's the propeller.
Oh yeah.
No, so to those amateurs on the call, definitely, when you go back to M13, old favorite, look for that. That was it was new to me, but it was one of those things that was fun to find.
Yeah. And like Dan said, once you see it, you'll never not see it when you look at M13.
Thanks, Dan.
Yeah. Is there anything else? It sounded, Dan, like you had some other things that you
Barrett
wanted
or
to.
something?
Oh no, I was just thinking of objects for Saturday night, and
Mhm.
I always tend toward the showpiece objects, and you tend toward the esoteric. So I think we have a great balance there.
And of course, I'm not going to steer the public toward the esoteric,
Oh, you
but
should. I think once in a while you get a really good look.
well, I think what I'm gonna do, depending on what scope I'm using, pretty please, probably something like the Foxhead cluster in Cygnus, which is a really nice one. I suspect people will be showing M11. I don't want to suggest things for people.
Oh, we should. I mean, this is a great time to kind of throw out, what are your favorite? I'm because I at least in past Dexter parties, I kind of rotate between 3 objects, and then and of
Mhm.
course that ends up on Saturn, and so
Right.
but Saturn won't be up until 11:30, so easily
We'll still
viewed.
be there.
Yeah.
Oh, yeah.
But so I thrown out a couple things, the obvious stuff, M13 and the ring,
Mhm.
or
Alberio.
Are you going to have your 20-inch there, Dan?
I think so, Andy, and I'll bring along the C11 on the tracking mount if you want something that'll be pretty hands off and easy to.
Yeah, that would be perfect because that way I won't have to get up and keep readjusting it.
Yeah.
So yeah.
Okay. That'll be a fair amount of that you can just pick something C11 friendly.
Yeah.
Hey, Jerry, did you get a hold of the people with the light?
No, I've forgotten to do that, but I'll give them a ring tomorrow. And the bushes have grown up enough to where that may not be as big a problem as in previous years, but I'll see if I can get them to shut it off anyway.